share the screen. Okay. Fine. Deleting a leaf node is simple. Deleting a node with one child, for example, tethered, is simple. Okay. If the element to be deleted has two children, then we take this largest element on the left subtree, and the largest element on the left subtree should have no children or one child. At least the right child should be missing for the largest element, right? Right child should be missing. So it is easy to delete this kind of value, the largest element. For example, here, to be able to delete red, the largest element on the right subtree is found, which is priest. And priest has one child, so it is easy to delete priest by making it to be right child of Milt. As you see, priest is deleted, and priest is replaces to the red. Now priest is there, right? So the smallest, largest element on the left subtree can easily be found and deleted. Since it doesn't have any right child. For example, priest doesn't have any right child. It cannot have a right child. If it has, it cannot be the largest element, since the right child should be larger than priest, right? And it shouldn't be there. This is the algorithm to perform removal operation. The algorithm is simple again. If 3 is null, we don't have anything to delete, which means the element is not found on the tree. So there is nothing to do as far as delete operation is concerned. If 3 is not null, we compare the item with the data at the local root. There are 3 cases. The equal case requires deletion, so it is left here. If the item is smaller, we perform deletion on the left subtree. If item is greater, we perform deletion on the right subtree. These are recursive operations. And if they are same, we have to perform deletion. As you see here, we use a delete return. Delete return is data field in the binary search tree class. As you see here, delete return is a data field in binary search tree class. So the element to be deleted, element which is deleted is stored in delete return. So it is a second return value of delete method, private delete method, recursive delete method. Again, public delete method cannot be performed recursively, since it gets a target only, and we have a recursive private delete method. And the second return value of this private recursive delete method is delete return, and reference to the item that is deleted is stored in here. So let's go back to the algorithm. In the algorithm, we found the item to be deleted in here, right? So delete return is set with the data at the local root. If the local root has no children, it's a special case. We set the parent of the local root to null reference. So the that child, left or right child of the parent, is not available anymore. If it has one child, for example, as in here, if this has to be deleted and has one child, the other child is null, then we set the reference of the parent to refer to the child, set the parent of the local root to reference that child. Okay. These are two simple cases for deletion. If there is one child, no children, or one child. If there are two children of the node, if the node to be deleted, let's say we have to delete this node, and it has two children, we have to find the largest element on the left subtree, right? If the node, which is the right child, has no right child, if this has to be deleted, right? This X to be deleted. Y is the left child, and right child of Y is not there if the left child has no right child. So Y is the predecessor of X. Then we can easily replace X with Y since it doesn't have any right child doing this, or it has this one, right? To be like this. This is Y. From here, let's make it this A, Y. This part is same, and this. We can easily delete X in this tree. Set the parent of the local root reference to the left child, as it has one child. Otherwise, now we know that the left child has a tree here. So we find the rightmost node in this tree, which is the largest element in this left subtree. And delete this and copy the value here into X, right? Copy its data into local root data and remove it by setting its parent to reference its left child. Since it doesn't have a right child, the left child should be a parent's right child. Okay, so this is the algorithm. Again, in this algorithm, we start from the root of the tree and traverse a node that has to be deleted. And after we find that this node has to be deleted, we traverse its largest value on the left subtree, and largest value on the left subtree is a leaf node. So the overall running time of this algorithm depends on the height of the tree. Since everything we do at each node is constant time operation, the running time depends on the height, and because of that, the best case running time is again deleting, for example, if we have something like this, and deleting this node will take constant time. It's a special case, but gives constant time. All the elements here is n, while deleting this special node takes constant time. So the best case running time will be constant, and worst case running time is to have such a tree and deleting a node here, which takes linear time. So the worst case is linear, but in general the height is logarithmic, so the running time is logarithmic in average case. As in search operation and insertion operation. And the performance of all these three operations are same in worst case, in best case, and in general case. The code is in the book on pages 325 and 226. I'm not gonna go over the code over there, but in here you can see that a binary search tree class is implemented. The values that is gonna be kept in binary search tree has to be comparable. Okay, and binary search tree class implements the search tree interface and extends the binary tree. So in binary tree, remember, we have a node inner class, so that information is inherited from binary tree. And the root is available in binary tree, remember. Or let me show the binary tree as well to you. Here it's a binary tree. Remember, in binary tree, we have, where is it? Root node as data field and a node structure as a, where is it? There should be a node. Where is node? It extends something as well? No. Node, there is a node class as well in binary tree. So binary tree has a node class as an inner class, and data field as root. These are inherited. Also, the methods are inherited, but we are going to use only these two pieces of information. So these are these pieces of information comes from binary tree. Okay, so we have two additional data fields, add return and delete return, to implement add and delete operations. Second return value of these two operations are these, right? We have seen so far. We have already talked about find operation, and it uses a recursive find method, which is over here. We have already talked about this. And add method, which is iterative, and it has to have a helper method, recursive help method, add method, which is over here. We have already talked about it as well. Okay, now we come to delete method. The starter delete method. It's a public delete method which takes a target value and returns a value that is deleted, and it returns null if there is no element. Actually, if it returns, it throws an exception if the target is not comparable as well. Okay, the object is not in the tree, then it returns null value. It returns the object to be deleted from the tree, or null if the object is not in the tree. After the operation, the object is not in the tree. Okay, we know that. It calls the recursive method. Recursive method has a node and an item as parameter, and returns the node, which is the root node of the tree, after the deletion operation. So it takes root node as a parameter. After the deletion, it returns the root node. So it has to be assigned to root after the delete operation. The return value should be assigned to the root, since the root could be modified after delete operation. The returned new root value has to be assigned to root. And return value is in the delete return. As I said, using such data field is not a good way of doing it. We may have an additional parameter to this recursive delete method to handle that probably. This recursive delete method has two parameters, the local root and the item to be deleted, and returns the modified local root after deletion operation. And after the deletion is the method returns the item is not in the tree, of course. The delete return contains the reference to the deleted item if the deletion is successful, or null if the element is not found in the tree. So delete return is there are two consequences of this operation. One, deletion is performed. Second, delete return is set properly. And as I said, the delete return is going to be used by public delete method. Okay, let's see how it is done. This base case is simple. When the local root is null, which means we couldn't find the item on the tree. So delete return should be null since we didn't delete anything, right? And we return the local root since it has to return something. It is the tree after deletion. The tree is not modified after the deletion since the element to be deleted is not in the tree. So this is a simple base case. After that, we compare the item with the element at the local root. If the compare result is less than 0 means the item is smaller. We perform the delete operation on the left subtree, and this deletion operation will return the new left subtree after deletion, and this has to be assigned to as a last subtree. Of course, during this deletion operation, add return, delete return value could be modified. That's fine. We are not going to use in here, but the callees may need them. So delete return is set by this recursive call, and local root is returned after this modification. Actually, local root is not modified here since we didn't change the local root here, but the local root's last subtree could be modified. Still, we need to return the new tree or the root of the new tree, which is not changed, but we need to return it anyway. It's going to be used by recursive callees. If the compare result is greater than 0, means the item is larger, then we perform the delete operation on the right subtree. As I said before, delete operation as in left subtree, delete operation on the right subtree should set the delete return and return the right subtree after deletion. So we make it to be right subtree by assigning to the local roots right. And return local root as before. Okay, so these are two cases where a recursive call is required. And the last case is where we are not going to use a recursive call. So you are not going to see any recursive call in here. Recursive call to delete operation. So since if it is not less than 0 or greater than 0, it should be equal to 0. Compare results 0 means we found the item at the local root. So delete return is set here. Since we found the data to be deleted, we set delete return. As you remember, delete return is set here as well. Then we make sure that the item is not in the tree, right? So delete return is set since we make sure that the item is at the local root. If the left subtree is null, that's a special case. If the left subtree is null, we may have right subtree or not. But in either case, we can make right subtree of the local root to be the new tree, so we can return the right subtree. Right subtree is the tree after the deletion operation. Similarly, if the left subtree is not null, but the right subtree is null, we can return the left subtree. Both are null is handled here. Right subtree could be null as well. Doesn't matter. If both are null, the local roots right will be null here and it null returned. That's fine. So if there is no left child, we return the right child, which can also be null. And if the right child is null, we just return the left child. So these are simple cases when at least one child is empty. And when we come to this else, we make sure that both childs are available. Now we are sure that the node has two children. So we have to replace the data at the local root with its in-order predecessor. There is a special case here as well. The in-order predecessor is the left child directly. If the left child has no right child, then in-order predecessor is the left child. You can replace the left child and as you see, the data at the left child is copied in the local roots data, and the left child is deleted by making left point to left of left. Okay, the left child is deleted in this way. And the local root is returned. Actually, local root is not changed. The reference is not changed, but still it should be returned. The only place that local root changes, as you see, the local root is not changed here, or here, or here, right? Local root doesn't change. As similarly, a local root is changed only when these cases happen, since we return the right or left of the local root. Otherwise, we return the local root that has passed as a parameter, as you see. Okay, this is another special case if the left child is the in-order predecessor, else we have to search for in-order predecessor of the value. We are going to perform this by using find largest child. We are going to find the largest child on the local root's left subtree of the local root. This operation find largest child will search for the largest child in this subtree, local root's left. And after finding it, it will delete that node, delete the data, and it will return the reference to that data. It will return the data that is deleted, which is the largest element in this tree, in this subtree, right? And it is assigned to local roots data. Since it is deleted, there is no repetition. It is already deleted. So we can just return local roots since the largest child can replace the local roots data, right? So we search for another processor IP and delete IP from the left subtree and replace the root data with this IP value. Okay, and all these are done with this line. Finding and deleting is performed by find largest child, and changing the local root data is performed by this assignment. Okay, the only thing left is how we perform this operation, find largest child. Find largest child is in here, as you see, in this place. Find the node that is the in-order predecessor and replace it with the with its left child, if any. So it deletes it, actually. So it has one parameter, a node. This node is the parent of possible in-order predecessor. So it is the parent, since we need parent to be able to perform deletion. So it's the parent. If the right child has no right child, so right child is null, means right child is the largest value. Means in-order predecessor. We get the data in return value that we are gonna return later on. And we perform this operation, right becomes right's left, to delete the right child. So this operation deletes the right child. The node is not distracted. As you all remember, it's gonna be handled by the garbage collector, right? This is the base case. If we have found the in-order predecessor, we perform this operation. We make sure that we find the in-order predecessor by this checking right child's right is null. Then we find the in-order predecessor as the right child and perform these operations. If we couldn't find yet, we perform a recursive call on the right child and perform the operation on the right child. So we implement find largest child recursively. The parameter is the parent. Since the right of the right is not null, we can make sure that the parent can be the right child of the parent. And we continue in that manner until this base case happens, until we find the in-order predecessor. When we find it, we save the value to return and delete it. And the return value of this recursive call has to be returned, of course. You shouldn't remember it. You shouldn't forget it, excuse me. You should remember it. You should be careful about it. So, as you see, the parameter is the parent of possible in-order predecessor, and return value is the in-order predecessor. And we make sure that after the execution of the recursive method, the in-order predecessor is removed from the tree and it is returned as a return value. So this is all about deletion. Do you have any questions? As you see, we have go over the binary search tree methods, especially delete method in detail. Find largest child is what we have covered as well. To be able to test binary search tree, we have to perform the operations and verify the in-order traversal is sorted order. If you traverse a binary search tree in order, it should be sorted order, and we should make sure that the elements are what we are expected as well. So when we perform an order traversal, the elements, if we perform this traversal after a deletion, the deleted elements shouldn't be there in this traversal, and the elements should be in ascending order, from smallest to largest. Okay, we have to perform series of insertions and deletions and perform all special insertion and deletion operations and make sure that the result is correct. Okay, this is it for binary search tree. If you have a question, you can ask now, or we can talk about your questions on Friday.
Sure, I have a question on delete, but I prefer asking next class, so maybe I can understand between.
Yeah, please look at these codes. All of them is in the book, so you can look at it. Please try to understand it, and if you have more questions, you can ask. Maybe Thursday is possible as well, just before the class. At the start of the class, you can ask it, or you can leave it on for the Friday if you have questions. Okay, any more questions for today? Okay, I see there's no question, so let me start recording.